Okay, let's finish chapter 5. Two topics. The first thing is, sorry, let me get my marker. The first thing is indirect proofs. So this is 5.5, and this is indirect proof. And the idea here, it's another way of proving something. So you're given a conditional statement. What you're going to do then is you're going to take that Q and assume the negative is true. Then what you're going to do is you're going to use that negative statement or the not Q to arrive at a false conclusion. At this point, you've proved, and therefore you can conclude that your assumption was false and that the actual statement was true. Here's an example. A scalene triangle, here's the statement. If a triangle is a right triangle, then it has no obtuse angles. So example 1, a right triangle has no obtuse angles. Now, the first thing you would do is write this as a conditional. So you would say, if a triangle is right, then it has no obtuse angles. That's the first step. The second step is assume the negation of the conclusion is true. Say, okay, assumption. A right triangle has obtuse angles. Well, let's work through. Let's assume that's true. Let's assume I have a right triangle. A, B, C. Okay, well, I'm going to let angle A equal 90 degrees, and I'm assuming. Now, once again, you're saying, Mr. Elliott, that's totally false. We're gonna get to a contradiction. So angle A is 90, and let's say that angle B is 90 plus some other angle. Let's call that theta. So it's greater than 90, and theta is going to be positive. Okay, and what should we call C? Let's call C beta, another random angle. That's fine. So we have our three angles. Okay, now what's the sum of the angles of a triangle? You say, okay, well, the sum is 90 plus theta plus beta equals 180 degrees. Okay, well, what do you notice? Well, it turns out that theta plus beta equals 0. Is this possible? And you say, that's my false conclusion. No, not possible. Not possible, and therefore our proof is finished. You say, because my assumption led to a false conclusion, my assumption is wrong. Because my assumption led to a false conclusion, the assumption was false. And therefore, you've proven, therefore, this is true. And that's the idea of an indirect proof. Now, a really famous indirect proof is something that's way outside the scope of this class, but we can kind of think about it just for a second. Something that's way outside is radical 2 is irrational. And so the question is, how do we prove that it's irrational? Well, we use an indirect proof. Now, indirect proof, an indirect proof says, no, assume it's false, assume radical 2 is rational. Now, I'm talking softly because it's late at night and I think my neighbor's sleeping. You learned last year that a rational number is a number that can be written as a ratio. Okay, the other condition about that fraction is it's fully reduced. So P and Q have no common factor except 1. That's fine. Okay, let's assume that I can write an irrational number, which you learned, I believe, last year, that it's those decimals that go on forever, and you can't write it as a fraction, but I'm going to assume it is. Okay, well, how do I get rid of a radical? Let's square both sides. So 2 is equal to P squared over Q squared. And then kind of cross multiply, and I have 2 Q squared equals P squared. Does anyone see the contradiction? Does anyone see the contradiction? Well, once again, it's advanced for this class, but I'll just say, look at P squared. P squared is something times something, right? But how could something times something be equal to 3 things? How could P times P equal to 2QQ? Right? So this is 2 things. This is 2 terms. And this is 3 terms. We have a contradiction. And therefore, radical 2 is irrational. Once again, very advanced, but that's the idea. So with any indirect proof, assume the conclusion is false and work through that. An example in the book might be prove that a number ending in 5 is not divisible by 2. So the first line of the indirect proof would be assume that there's a number that ends in a 5 that is divisible by 2. Immediately you run into a contradiction, and that's the idea of indirect proof. Okay. That is a 5-5. So it's another technique. So now we have 3 techniques for proving. We have deductive reasoning, we have coordinate geometry, which we're going to get back to, and we now have indirect proof. Okay. Now the last unit is chapter 5-6, and it has to do with triangle inequalities. So 5-6 has to do with triangle inequalities. And this is really cool. Now the book develops these theories. I'm just going to tell you, and it may seem really obvious, but once again, everything that we do, we have to build up to. The first thing is, given any triangle, if you have 3 sides, and let's say opposite side A is angle A, opposite side B is angle B, and opposite side C is angle C, if side A is less than side B is less than side C, then, and actually it goes both ways, then angle A is less than angle B is less than angle C. Once again, it seems obvious, but we know that we have to prove it, but we don't have time for that. Once again, the order of the sides corresponds to the order of its opposite angles. So, if you have a triangle, let's say a right triangle, so therefore, we know that the hypotenuse is the longest side. And it's the longest side because it's opposite the biggest angle. We know that, so for example, in an equilateral triangle, let's say, 3, 3, 3, because all the sides are equal, all the angles are equal. Kind of cool. Okay, and then the last part, this is great. This last part is great. Okay, it says that the sum of two sides of a triangle is always greater than the third. So let's look at two triangles. The idea is, if you have A, B, and C, it says that A plus B is greater than C. It says A plus C is greater than B, and B plus C is greater than A. Now the visual I use is I imagine that, let's see, all these are all the same. If you have two sides of a triangle, the third side cannot be equal to the sum, because then you wouldn't have, it would be like extending out to a 180. You can't have that. So the two sides have to be greater than the third side. Once the third side is equal to the two sides, you don't have a triangle anymore. And so I might give you two examples. So I might say, is this a possible triangle? 3, 4, 5. Now, of course, you might recognize it as a right triangle because it's a Pythagorean triplet. But we know it's a triangle because it's a possibility, because 3 plus 4 is greater than 5, and 3 plus 5 is greater than 4, and 4 plus 5 is greater than 3. So yes, this is a possible triangle. Now, a lot of times you make fun of me because my diagrams are really bad. So let's say I just draw a triangle down like this, and I say 1, 2, 9. Is this a possible triangle? I mean, I wrote it down on the paper, so it must it be true? And you would say, no, Mr. Elder, it's not true. You say, well, 1 plus 9 is greater than 2, and 2 plus 9 is greater than 1, but 1 plus 2 is not greater than 9. So this is not a possible triangle. Not possible. And then a fun question to think about is, given a triangle, can you see it? Yeah. Given a triangle over here, one side is 3, one side is 7, and the other side is x. What are the possible values for x? So I want you to think about that. I close the door. Well, it's fine. Okay, so you've thought about it. Well, there's two cases. Either A is the longest side, or it's not the longest side. So let's see. If x is the longest side, then 3 plus 7 has to be greater than x, or x is less than 10, right? Well, what's another condition? Maybe 7 is the longest side. That means, or 7 is the longest. Well, that means that 3 plus x is greater than 7, or x is greater than 4. Therefore, we combine the inequalities, because we have a compound inequality. Two conditions must be met. X has to be greater than 4, but less than 10. And that's the end of chapter 5. I'll put it in an assignment and we'll decide what problems we can do. Good.